So yesterday we talked about two models, two dynamics, the snatched dynamic and the water dynamic, and we studied them using simulations, and we deduced some equations to try to understand slightly better the dynamic. And we saw that we got two equations. One was a diffusive equation, like heat equation more or less, and for the water model, and the other one was a transport equation for the snatched model. And both of them, of course, are very different, yeah, qualitatively and in all the properties and everything. But the nice thing is that from the simulation, we already knew that we were going to encounter two kind of very different equations. And yeah, the way we deduced the equation yesterday was not very rigorous. It was more like informal, heuristical, but it gave us the right way to think about these things, because at the end we just look at the master equation, which were only a balance between a gain term and a loss term, which is more or less very natural, right? If you think of the way we used to deduce the heat equation, we make this kind of balance between heat going in our domain and heat going out our domain. So this makes a lot of sense. This is not very weird. So now what I would like to do today is to come back to this kind of transport equation we get. Yeah, something like that. Here I put the equation we got yesterday for the snatched dynamic. And yesterday, just I mentioned you some. There is a. Here I got. This is this shouldn't be here. It's just a typo. Sorry for that. And the thing is that this equation is not very complicated if you were smooth. But the thing is that we saw yesterday that U in our setting was a probability distribution. A probability distribution over all the possible value of the magnetization. Magnetization, it was a parameter we used to characterize the state of the system. So if U is a probability distribution, there is no reason for you to be smooth. Yeah, a probability distribution is just an arbitrary measure, non-negative measure with total mass equal to 1, but it could be highly singular, right? And the transport equation has no regularizing effect like a diffusive equation. So if initially my U is singular, it remains singular in time. Okay, so it's not that obvious how to solve this kind of equation, right? And moreover, I told you yesterday that I put you the solution of this equation when U was smooth. Okay, but yeah, nice solution, nice an explicit expression, but which maybe is not very helpful to understand what happens. And the main point here is that what happens is qualitatively completely determined by this expression here, this vector field here. And this is, in essence, the characteristic method, which is very standard method we saw in courses, undergraduate courses about partial differential equation. And the good thing is that the same method can be used to solve this kind of transport equation when we are dealing with non-smooth equations like probability distributions. So what I would like to do is to review slightly this characteristic method easily. Nothing will be very complicated. Just get to show you the main idea, and we will try later to use this idea to solve in general this kind of equation. But it will be in essence exactly the same idea, but with maybe some technical twist in the middle. Nothing more. And then at the end, what I would like is to mention a little bit what we could do when the expression with. So we will be dealing with this kind of equation, right? Transport equation with here a vector field, yeah, will be working in RD in D dimension because it's the same as in 1D. Okay, no more difficulties, and we'll see how to solve that. And at the end, what I would like to do is to mention what we can do when this vector field V depends on the solution U itself. That give you at least an example where this kind of equation pops out. This is not just for the sake of mathematics. It's really useful, and it comes very naturally in a lot of settings. And see how what you can do here, but very quickly without much technicalities. Okay, just giving you some references if you're interested. So we are dealing with this equation, right? And V here is a given vector field. Okay, and this kind of equation is usually known as a conservation law because it expresses in mathematical way the fact that some quantity is conserved in time. Okay, so and this is exactly the idea behind all the characteristic method. So I would like to see what I would like to show you a way to deduce this equation very easily, which is not the fastest way, but for me it's more illuminating, more interesting, because it gives you exactly the right feeling, right? So the idea here is that we are thinking that we have a bunch of particles, okay, moving in time, following through due to maybe a force exerted by this vector field V. Okay, so it's as if I had a river, and into that river I just I throw some ink. Okay, and the ink particles are moving along with the stream of the river, the stream of water, right? And the stream of water are just the trajectories of the vector field V. So this is exactly the method characteristics, because we are following each ink particles, its trajectory, and see at each time what do we get. And if there is no creation or destruction of mass, if I don't add any more ink, or if I don't pull out any ink from the river, then the density, the distribution of ink at time t in my river, this would be my U here, would solve this equation. So how do we put that mathematically? So let's see. We need the notion of we need the trajectory of the vector field V. Okay, this just means that I need to solve the ODE associated with my vector field V for any initial condition x, right? And this solution, which in V is globally Lipschitz, obviously exists for any time t in R, not necessarily t positive here. And this solution, so I will always assume that V is globally Lipschitz. If not, it gets more complicated. So let's put just V global Lipschitz, and that's it. It's easier that way. So I can solve this ODE, okay, at least theoretically. And the solution I will denote it by t sub t of x. Okay, so x indicates the starting point, and the sub-index t indicates time, right? So this only means it's nothing complicated, but everything is here. Everything that matters is in that definition. We only have to understand how these trajectories t sub t of x, how do they relate to my transport equation. If we understand that, we're done. So this only means that I'm starting at x at time 0, and my point x just travel in space due to the forces V here, check, and at any time t, I'm here at t sub t of x. All right, and the arrows are V as here it would be v at the point t sub t of x, right? So this is very standard, nothing complicated here. And this t sub t is usually called the flow of the vector field v. And since v is global Lipschitz, there is a unique equation. So you got that t sub t is a bijection from RD to RD. And to have the inverse, it's easy. You just have to reverse time, right? Because if I got here at y, to go back, I just need to go backward from y to x. I just need to reverse time, and that's it. Okay, and only as a and also a consequence of the existence of uniqueness, you've got this semi-group property of the flow, which means that if you want to go from x at time 0 to some point at time t plus s, you can do that in 2 steps. You can do that, for instance, moving along for time s, and then when you arrive at ts of x, you just forgot what you did, reset clock, and just move along for time t, and you will arrive at the final position you would get if you had traveled in one way, in one shot, for time t plus s. So nothing big, okay? But this is the only real concept I need. This is the most important one. So it's very basic, but it's very useful. Okay, so we've got the trajectories of one particle. So now, just what we could do would be to pick some piece of space. Okay, let's say this is my piece of space U. I pick all the particles, all the ink particles in U, and follow their trajectories for a time t. Something like that, let's say. And doing that, at time t, we would arrive at t sub t of U. Okay. Okay. And saying that the mass is conserved, if there is no destruction or no addition of mass, this only means that the total mass I had in U at time 0, which is this integral here. Remember that small u is the distribution of particles at some time t, right? My density of particles. So this total mass I have in U at time 0 is equal to the total mass I have in this set at any time t, right? I'm just saying that globally, I didn't lose when I'm tracking down all the particles that are initially here. I've got them all here. Okay, I didn't lose anybody. This only means that, right? Okay, so we are just saying that at the end, this quantity here is conserved. The total mass I have at n time t is conserved. So its derivative is 0, and I would just like to compute this derivative. And computing this derivative, I will see my conservation law, my transport equation will appear. Only that. And since the derivative is 0, this will give me my transport equation. Right? So I repeat, it's not the fastest way to deduce the transport equation, but it's useful. I guess it gives you some feeling of what's happening because you are just following particle along time. Okay, so how could we compute this derivative? So we'll do it very basically in an elementary way. We just look at the value of this integral at time t plus h, t plus small h, and we'll make a Taylor expansion in h. And the other one term in the Taylor expansion will be my derivative. Only that, right? So I look at the total mass I've got at time t plus h. Sorry, t plus h. It would be nice to recall that we have this semi-group property. So to arrive at time t plus h, I only have to move forward for time t and then move for small time h. Okay, so this is only that here, and we make a change of variable, and we've got that. Okay, so now I just want to make some Taylor expansion of that quantity when h goes to 0. Okay, so it's easy. We just have two terms here. We make Taylor expansions of these two terms, put everything back in that expression, and that's it. Okay, so it's not complicated at all. And see what happens. Okay, so the first thing is that, well, for a small h, th of x, remember that th of x is the trajectory of x. So when I just move a small time from the initial position, I'm at the initial position plus h time my velocity. Right? So I put that here, make my Taylor expansion, got that. Okay, so easy. Then the second term is, what is the second term? The second term is this determinant, the Jacobian. Okay, maybe a little bit more, not that easy. So I just need to understand this differential here, right? So we could come back to the definition of pH of x, which was given through this equation here, and differentiate it with respect to x in this equation, right? That way we would get this equation, and from that we get this expansion for the differential of pH, okay, which is the identity. It's normal because t0 is the identity, and okay, so the differential of the identity is the identity plus a small increment h. Okay, then we took the determinant of that, and it's an easy, it's very easy to check that the determinant of the identity plus a small perturbation is 1, the determinant of the identity, plus the trace of the perturbation. And the trace of the differential of V, the gradient of V, is the divergence of V. So that's it. We have the two expansions we need here and here. So we put them together, just rewrite things a little bit. And here we've got the other h term, which is exactly my transport equation. Yeah, the time derivative of u plus divergence of v times u. Okay, so, and you see it comes very easily, right? Because in the divergence of u, there is the gradient of u coming from here, which comes from the changes in u, plus the divergence of v, which comes from if the flow is expanding or contracting volume. Okay, right, so got everything together. We come back to our expression, which was this one. And since now, since now we know how to expand this, we've got this, right? And then, so we've got the Taylor expansion of this integral. The total mass at time t plus h is the total mass at time t plus another h term. And this term of order h is exactly my derivative. And which says that this derivative should be 0 if just to express that mass is conserved. Okay, if there is no creation or destruction of mass. So since we do this for any piece of space U, and since T sub T is a bijection, then we got that what's inside the integral is 0. Okay, so that's it. We make the deduction of we got the transport equation as a conservation law. Now we understand that really it's a conservation law because it just mathematically says that something is conserved in time, something which is moving along the trajectories of V. Okay, this is nothing less. Okay, and nothing more. So that's good because we understand what physically this equation is saying. Okay? And most importantly, we understand that to solve this equation, we just need to keep track. We just need to follow the trajectories of V. We just need to follow these curves in space for any initial point X. And this is the only idea behind the method of characteristics. Okay? And here everything works fine because V is global ellipsis. Okay? Otherwise, yeah, could not be that easy at all. Okay, so that's good. So now we've got the intuition. Okay, so let's come back to the transport equation, but now in the measure setting. So this means that my initial condition is a probability measure. Okay? It could be a measure in general, not necessarily a probability measure. There are small changes to make at some point. I will just say a word about that later, but it's no big deal. Okay, but I prefer to stay with probability measure because this is a framework we came up with yesterday. Okay, so it's more consistent. So we have an initial probability measure, which is the initial distribution of my quantity, which is conserved in time. Okay, and then I want to solve this equation, this conservation law, this transport equation. Right? So first thing, since mu0 is a probability measure, and since we know in general that first transport equation do not have a regularizing effect, we cannot expect mu t to be smooth. So we have to understand this equation from a weak point of view. Okay, so I will take this definition of being solution of this equation. Okay, so here phi is just a test function, and as usual, to get this, you just take this equation here, just multiply by phi here and here, and integrate by part. And the divergence, when you integrate by parts, goes to phi as a gradient. Right? Okay, so this is my definition of a solution, plus I will need to add later some kind of continuity of my solution with respect to time, because at the very least, I would like my solution to go towards the initial condition as time goes to 0. So I will need some kind of continuity, meaning that I will need some kind of topology on the probability measure. Okay, so we need to discuss a little bit that issue slightly later. Okay. So for now, I just want to concentrate on solving my equation in a weak sense, following the intuition that the method of characteristic gave me, which is I should take my initial distribution mu0 and move it following the trajectories of my vector field V. So how can I just put that mathematically? The fact that I would like to transport my initial distribution along So we are saying that we want to solve this equation for any initial condition mu0, any probability measure mu0. Okay, but since I still don't understand much what's going on, maybe it will be better to start easy. I will not take any initial condition user, any probability measure user. I will take an easy one. An easy one would be, for instance, a direct mass. So I take a direct mass here, meaning that all my distribution is concentrated at one point, which is x naught. Okay, and the method of characteristic is telling me just move along with the flow of the vector field. So if I move along, if I move forward with the flow, maybe it would be a good idea to look at the direct mass located at this, at this point, because this point is exactly the trajectories of my starting from x naught, right? So really, I'm just following the intuition we saw a few slides earlier. So just let's check that this mu t really is a solution. Okay, so I take a test function phi, and I would like to compute the derivative of this integral. So what is this integral? Well, easy. Integrating against the direct mass is only evaluating the function at the point of the direct mass. So since I'm looking at the direct mass located at this point t sub t of x naught, this integral here is just phi at that point. Okay, easy. So I take the derivative, right, which is this one. I remember that t sub t of x naught is the trajectory of v, so this means that this derivative here is exactly v. And now I just have to write this expression back as an integral. But you see that this expression is nothing less than the function gradient phi times v evaluated at this point t sub t of x naught. So this is only this integral. So that's good, because this equality here, because between this derivative and this integral, tells me exactly that this mu here is a solution. Okay, I say a solution because still I don't have any uniqueness results. Just I'm working slowly toward, at the end, a nice, well-postmath result. I would like to have existence, uniqueness, and it would be nice to have some continuity of the solution with respect to initial data. Right? Okay, so now we're just looking at the existence part. So now we know how to solve this equation for one direct mass. We could do exactly the same, taking a convex combination of direct masses. Okay, and in that case, what do I have? A convex combination means that the coefficient here ai are non-negative and sum 1. Just because I want mu naught to be a probability measure, to be non-negative and having total mass, which is the sum of the ai, equal to 1. Right? So this only means that I'm just making this kind of picture. All the mass is distributed among some points. Okay, each point share some percentage ai of the total mass, and we are moving each point follows its trajectories. Let's say something like that. Okay, and we are just saying that exactly with the same two lines of computation we just did, we can show that this expression here is a solution. And you see, this is exactly the same logic as before. Just each point xi, I'm following it. I'm looking at its trajectories, t sub t of xi. Right? The same logic. But this is not bad, because any measure, I can write it, I can approximate it that way. So this tells me that I can hope to get existence for any kind of probability measure as initial condition, because if at least I can solve my equation for any initial condition of this form, I'm very close to grasp any kind of probability measure. Actually, we could write something slightly informally in the way that we could say that my mu0, I could write it that way. Delta x, sorry. Delta mu of 0 of x. Could write something like that, saying that this would be the generalization of this finite convex combination. Okay, I replace the sum by an integral, and I put this is the integral of direct masses, and to each direct masses I put this weight here. And actually, this could be justified. This is just the integral of a measure-valued function. So this could we could make sense of that. Okay, and in that case, what would be the solution? The solution would be something that with the same intuition as before. Delta t sub t of x d mu0. Okay, so we could make sense of that. In a much direct way. Okay, but this gives me the right intuition. Okay, so let's say, how do we proceed? So we saw that with this example of a convex combination, we just need to go along with the flow, right? So we need just a basic concept of measure theory, which is a concept of the push forward of a measure let's say mu, by a function t. And look at the name, push forward, which means that just send forward your measure mu by this function t, which is exactly intuitively what we are doing, right? And the push forward of a measure in general is a measure defined. You can define it that way, say just saying that the push forward t sharp mu of some set A is this. Okay. But the most and this is equivalent to this formulation, right? It's exactly the same. But I prefer the second formulation because this is the formulation that I will use really. So let's take that as a definition of the push forward of a measure. And with this definition, you can check easily that really the push forward of a convex combination is exactly this thing. Okay, this is just an easy check, really easy using this definition here, nothing else. But let's say, look at the solution we got before. This solution here is exactly this expression, taking for t the flow t sub t, right? So we are saying that the solution we got for this very particular initial condition is exactly the push forward of mu0 by the flow t sub t of the vector field. So this is exactly the concept we used in the deduction of the transport equation. Okay, just keeping track of the trajectories of each ink particles inside the rib. But now we've got a nice mathematical framework to do that. Okay, just take the push forward of your initial condition by the flow. Right. So let's check that this works really. Okay, because we only checked it for a convex combination. So in general, we take an initial condition mu0, okay, mu naught. We take the push forward of this mu naught by the flow, and just let's check that this works. Okay, so we take the test function phi with C1 with compact support. and we need to compute the derivative of this integral. So first, what is this integral? Okay, so this is the integral of phi against this measure. And by the very definition of the push forward, this is exactly this expression. Okay, this is a definition of the push forward. Right. So now we can just take the derivative, okay, easily, because phi has compact support, so you can apply dominated convergence theorem, no problem. And as before, we remember that the derivative of the trajectory is exactly the vector field, the force, v here. And now we go back using again the definition of the push forward, because here we are integrating the gradient of phi times v at that point, which means that this is exactly this integral, again by the very definition of the push forward. And if you look at this computation, this is exactly the same computation we did before with the finite convex combination, except that here we have integrals instead of sum. This is the only difference. Okay, that's good because we got a solution. Maybe we should check two minor things just to be sure, because we started with a probability distribution, right? So it would be nice to have at any time a probability distribution. So it would be nice if mu t would be a probability distribution and not just an arbitrary measure. Okay, so I would very much like mu t to have total mass equal to 1 and to be non-negative. And this is obvious, completely obvious, because just to check that mu t has total mass equal to 1, I just have to integrate the function constantly equal to 1, use the definition of the push forward, and this gives me the total mass of mu 0, mu naught. And since mu naught is probability measure, its total mass is equal to 1. So that's it. And to check that mu t is non-negative, it's easy. I just have to check that the integral of mu t against any non-negative function phi is itself non-negative. And again, this is obvious. We just again use the definition of the push forward, and mu naught is a non-negative measure. This function here is non-negative because phi is non-negative, so my integral is non-negative. So I'm good. So up to now, so far we got, we have, what do we have? We found us for any initial condition, we found a solution, at least one solution, which is pretty nice, okay? So now how could we, just checking time, okay, good. Okay, now, what could we ask? Maybe it would be nice, we are lacking a few things. We are lacking maybe some continuity of the solution with respect to time. Okay, just because when time goes to 0, at least I would like my solution to converge, my mu t to converge to mu naught, the initial condition. I still need uniqueness, and I still lack continuity with respect to the initial condition, right? But the good point is that up to now, we've got a nice solution which intuitively is easy to understand. Just move along with the trajectories of the vector field. And that's it. Okay, so let's say a word about time continuity of mu t. Okay? Meaning that, for instance, if t prime goes to t, I would like mu t prime to converge to mu t. So I need a topology on the set of probability distributions, probability measures. And let's say, what could we do? So in general, when we have a bounding measure, okay, maybe the most natural norm to consider is the total variation, which is defined by this expression here. And this only means that we are looking at the space of bounding measures, bounded Borel measures, as the dual space of the continuous bounding function. Okay. So we see measure as a linear operator acting on continuous bounded function. With the here, this norm here is exactly the strong dual norm of the dual. So this is nice. This is very common. It's a nice norm because it gives you that the space of bounded measure for this norm is complete. Okay, so we got a balanced space. So pretty nice. But maybe it's not, but it's a very strong norm. It's not easy. First, it's not, we'll see that continuity here with respect to that norm is not very suitable for us easily. And the other thing is that it's not easy at all to get compactness with respect to this norm. So not getting compactness easily is a big issue usually. In any kind of approximation argument, you need compactness. In any kind of minimization of finding critical point of functional unit compactness some way. So not having compactness, it's not good. It's not that good. But just behind compactness, there is a very simple reason why this is not a good norm for us. Because just remember that the simplest case we looked at, when mu naught is a direct mass, okay, located at x. Yeah, then we know now that this measure is a solution. So I need this measure to be continuous in T. At least this is the simplest case, right? But the thing is that when I look at the distance in the total variation norm between two direct masses, if these two direct masses are located at two different points, then the norm is equal to 2. Because I only have to take a function phi equal to 1 at one point and then equal to -1 at the other point. And so I got my supremum is equal to 2. So not good. Because even if x and y are points in space very close one each other, the distance of the direct masses are far away. So not good. Okay, and in particular, when t, since this expression here is continuous in t, even with that, I won't get that my mu t is continuous. So this is not a good norm for us. We need something weak, and something weaker is the weak convergence. Or maybe it may be more appropriate to say it's a weak star convergence. Okay, from a functional analysis point of view. So in that case, we say that if we have a sequence of bounding measures un, we say that this sequence converges to a measure mu if we have convergence against any bounding continuous test function. Okay, but we do not require any kind of uniformity with respect to phi, as in the total variation norm, where the norm was the supremum over all the test function phi with less between -1 and 1. Okay, here we just require something much weaker. Just require for any given bounding continuous function, I need convergence. Okay, which is pretty weak. So later today we will see a distance, which gives you this weak convergence, which is the Wasserstein or Moshkontorovich distance. So a lot of them will use one of them, but there are also a lot of distances giving you the weak convergence. And this is the right notion for us. This is the right notion of convergence. And as far as I can say, in general, in the works I did dealing with transport equation for measure valued function in any kind of settings, motivated by open information process or biology, weak convergence is nice. Really, it works well. Okay, so for a practical use, it works. Okay. So let's say why is this the right notion of convergence for us? Well, simple. Let's say I would like to show that mu at time t prime converge to mu at time t when t prime goes to t. So I would very much like to show that for the weak convergence, this means that I just need to pick one test function phi and look at this integral, right? And I would like this integral to converge to the integral phi against mu t, okay, which is this expression here. I just forgot to write the integral phi against mu t. Maybe I should write it now to be better. So this is exactly, just I forgot to write it. Like, I will write it later. Okay. And here this is very easy because again, using the definition of the push forward, this integral here is just this one here. And now you pass to the limit just using Dominic convergence, nothing else, because phi is bounded and mu naught is a bounded measure. So everything works fine. So easy, because I do not require any uniformity with respect to phi. So things works well. Okay. So that's good because up to now, what do we have so far? So far we have a solution for any initial condition, and we know the solution is continuous in time for the weak convergence. And I will always assume that I use weak convergence, yeah, okay, for probability measure as a topology, right? So maybe I will need something else, something more, which is uniqueness, right? So let's look at uniqueness. This is only, I guess, it's this slide, and maybe it would be good to make just a slight short break of, let's say, 10 minutes, at least for me. I hope you don't mind. So just let's look at uniqueness. Okay. So we will need uniqueness. Nice. How do we prove uniqueness? Well, this is a linear equation. So if we suppose we have two solutions starting from the same initial conditions, then if we make one solution minus the other one, we got something which is still the solution of this equation, but with initial condition equal to 0. Okay, so what we would want to show is that if we have solution of this equation starting from 0, that is initially we have no mass, then I would like my mu t to be 0 at any time t, right? I don't want any mass to appear magically from nowhere. And this is easy to show. This is true, and this is very easy to show using the duality method. It's a big name for here. It's almost nothing, you will see. And all the details about that you can find them in a book by Cedric Villani about optimal transportation, topics in optimal transportation in chapter, I guess it's chapter 5. There is a theorem here which is more general that put in a more general setting than mine here, but essentially the same, right? So obviously the book has a lot more stuff, very interesting stuff, but this is the only thing I need for the moment. Okay, so let's see this duality method. So I would like my mu t, so I pick some time t, and I called it capital T, and I would like my mu t to be 0. So this means that I would like this integral to be 0 for any test function psi. So I pick one psi, and what I need is I need to take phi, which is the solution of this equation. And why is that? Because you will see here that it's very natural, and because you see that this operator here is up to a sign is the adjoint operator of this one here. Okay, so this is why it's called duality. So what do we do now? Let's just compute the derivative of this integral. Easy to do, right? We could do that. It's almost like taking the derivative of the product. So we take the derivative of phi, which is here, and then we take the derivative of mu with respect to t. And here, taking the derivative mu with respect to t means that we just write this integral here. Okay, so just now put the two integrals together, right? Just we put them together, and we've got the integral of this function against the measure mu t, right? But this function here is 0 because that's how we define phi. So all this integral here is just the integral of 0, so it's 0, of course. So this means that this quantity is conserved in time. So what its value at time capital T here, because remember that phi at time capital T is my test function psi, is the same as its value at time 0. But at time 0, mu is 0. So at time 0, this integral is 0, and we're done. We just have that this integral, we just proved that this integral is 0 for any test function psi at any time t. So we got uniqueness. So maybe just let's say a word about how do we find this function, which again is the characteristic method, but here much easier because we are in a smooth setting because psi is a smooth function. And how do we find that? Easy. We just have to again follow the trajectories of v. It's always the same idea. And what does that mean here, following the trajectories of v? Just I evaluate phi along the trajectory of v. So just take this derivative here, which is this one by the chain rule, and this is 0. Okay, so I want that to be 0. Okay, so this means that I want this function to be constant in time. So I want that to hold. And then, since my flow T sub t is a bijection, I've got this candidate as a solution for my equation, and we can check easily that this is the right solution. Okay, so I just show you how you can find the right candidate. What do we need? What do we want? What property phi should verify? Right. So that's it. This was just a small. Okay. So we are good. The duality method works and gives me uniqueness. So it's pretty neat. So what do we have so far? Well, so far it's pretty nice. So far we have that for any initial condition mu0 probability measure, we can solve this equation uniquely in this space. And we have an explicit solution which is given by the push forward of the initial condition by the flow of the vector field, meaning intuitively that we are just pushing forward the initial distribution following the trajectories of the vector field V. So that's good. We got existence, uniqueness, and we know precisely what is the solution. This is pretty good, right? So what? And now, if we come back to once we know everything, we can come back to the equation we found yesterday for the Nash dynamic, which was this one, right? You should ignore this because it's a typo again. We should ignore that, and this is my vector field here, right? And so we suppose that we can solve this equation because now we know that u at time t is exactly the solution. The time here is tau because if we remember yesterday I had to make some time rescaling, but no big deal. But we know now what is the solution. Just the push forward of the initial distribution by the flow of the vector field, right? And to understand qualitatively the dynamic, you just have to understand how are the trajectories of V. And this is easy because to know how are the trajectories of V, you just have to look at the sign of V because we are in 1D. And the sign of V is given by this M here, meaning that if we are where M is positive, V goes to the right, and so the trajectories are going to the right. And if we are on the negative side, we are going to the left, right? So since the initial mass, let's say is this thing here. This is my initial mass. Since this initial mass is moving along, following the trajectories of V, all the parts of the initial mass which is on the positive side will travel towards the right, and all the mass which is on the left side will travel to the left, right? And when do that stop? That stop when V is equal to 0, and V is equal to 0 when M is equal to 1 or minus 1, or when M is equal to 0, which means that if I have a direct mass at 0 within my initial distribution, then this direct mass stays quiet, doesn't move, right? But except for that, the only thing that is stopping the dynamic is that the vector field V is becoming smaller and smaller when I come closer and closer to 1 and minus 1, meaning that my mass will now accumulate at 1 and minus 1, forming two direct masses. And I know precisely what direct mass is. These direct masses are the direct mass I will have at 1 will have a coefficient equal to the initial total mass in on the positive side. And my direct mass at minus 1 will have coefficient equal to the initial mass I had on the negative side, meaning that I should have this, that ut should be going as time goes to infinity toward a convex combination of a direct mass at 1 and a direct mass at minus 1. Should make some more space, and I will write that more cleanly later. So I will have a dynamic mass at 1 plus the direct mass at minus 1, and assuming there is nothing at 0 initially, just to get rid of that, the coefficient here would be the initial mass I have on the positive side, right? This is on the plot. This is the green part, okay? And going to minus 1, this is the pink part. I have all the mass which was initially at minus 1. Oh, sorry, I did something wrong. Yep, there, which is here. So you see, this is pretty cool, because with this very simple method of characteristic, which is very standard in any PD undergraduate PD course, we can adapt it to deal with a transport equation for measure valued functions, which is not that trivial at the first sight. And we have a clear understanding of the qualitative dynamic, what's happening, and we don't even have to solve it explicitly. It's pretty good. We don't have to find explicitly the trajectories of this vector field. We could do, because this is not a very complicated equation ODE to solve. We will have to solve this equation: m prime equal to m times 1 minus m square, and you can solve that, and this would give you the explicit solution I showed you yesterday. But this is not very helpful to understand the dynamic from a qualitative point of view. Whereas this here is cool, because just looking at the trajectories of V, and in 1D it's easy. We just have to look at the sign of V to understand if V is moving things to the left or to the right. We just have a clear understanding of what's happening. Okay. Okay, so up to now we have existence, uniqueness. We saw we have the right topology to work with on probability measure, which is a weak convergence of measure, the convergence against bounding continuous functions. And we will need, it would be nice if we could have some continuity with respect to the initial condition. And just nice from mathematical point of view, but later we'll see a clear application of that. Okay. So for that, it would be good to have a distance on the set of probability distribution, and this will be a nice one is the Morse ontology. But before going to that, if you don't mind, I very much like to make a short break, let's say of 10 minutes.
Oh, of course, of course.
Yeah, if you don't mind, because I'm quite hungry actually. And so let's say it's I've got 12, 5 past 12. Let's say we could resume at a quarter past 12. Yeah.
Okay.
If you're okay with that, around that, yeah.
Okay,
and
5 minutes.
Yeah, 5 to 10 minutes of break, just for me.
Okay.
It should be. I would like that. So
Okay.
if you don't mind, because yesterday I did everything one shot, and maybe it might not be the better way for anybody. So let's try with a break. Oh, okay.
Bye.
So just see you in 5 to 10
you.
minutes, everybody. Thank you to just keep up. Thanks.
See you. Hi, Julio.
Hi, Cheese.
Everything's okay?
It's okay, more than okay. Very interesting. YouTube, it's all over. Okay.
In the YouTube, okay. In the record,
yeah.
Okay.
Yeah, the record is okay. Our beautiful faces right on YouTube.
Okay.
So it's just matter to Nicolas, and it is on.
Juliana, don't give your face today.
Yeah, she's a little bit shy today.
No Juliana, no Pamela.
Just a quick announcement. Taking advantages of Nicolas' break, and to everybody present here, we remember that we have today in the afternoon the 2 invited talks given by Professor Ariela and Professor Antonella. You can go to the webpage or see the abstracts and so on. So we are cordially invited to stay with us for the afternoon session today.
And tomorrow, it's nice to talk about tomorrow.
And it's also important to remember the audience that you can see to the poster session we already have in the YouTube channel and the webpage. Give a quick view on them. There is a beautiful works there too. So if you don't mind, I'm going to get me a coffee and I'll be right back.
Okay.
So this I have a question. I'm reviewing your website right now, and I guess it's off air. It's not on the air. It's not working.
Oh, working.
I
But
don't know if it's my device or it's in fact our website.
let's talk with the technical support. Website maybe is out of. Is off.
Right. I listen.
Okay. Okay.
Yeah, I took the 5 minutes, the 5 Brazilian minutes.
No.
Yeah, I
It's
didn't
okay.
realize time. And just I look at the watch. I should. Okay, all right.
No, everything
Okay,
okay.
so I guess I. So if you're okay, we could resume.
Yes, yes.
Good.
Before to resume, if I may, I have a question. It's more out of a curiosity. When you say that we already have the ideal topology to get aboard with this master equation, you named the weak star convergence. Okay, of course, you're dealing with measures is natural, but we have another more natural, which is the Wasserstein's matrix.
Yes.
Because we are at the end, we are in a mass transport problem. So why not to adopt that direction?
Yeah, because I will use now the Wasserstein metric.
Ah, okay. So I'm
Just
going
because
ahead.
I didn't need exactly to introduce the distance to have to state the continuity in time, but now now that I want to have some continuity with respect to the initial condition, now I would like very much to have distance. And the good one would be the one of the Wasserstein distance, W1, I will use. And you have some variant like the bounded Lipschitz norm, which is useful too in other contexts, but they all share the same idea globally. But
Okay.
you're right, you're right. Just a slight thing is that Wasserstein distance doesn't give you exactly with convergence, because you have convergence against continuous functions that may grow for W1 linearly. So it's not only for bounding continuous function, but you have to restrict yourself to measure with finite first order moments. So for W1 to be well defined, only that. But just I will. So it's no big deal. If you take compactly supported measure, it's all the same. So
Yeah.
and usually people do that. So do not care. But
Yeah,
you're right.
okay.
You're so completely right. So just now you mentioned that. So let's go back to where here. Let's go back to this issue of having some continuity with respect to initial condition, which means that if I have two initial conditions, mu naught and nu naught, I got the corresponding solutions, right? Mu t and nu t. I would like to have something like where the distance between mu t and nu t is less or equal than some constant time the distance between mu naught and nu naught. Exactly the same kind of things we have from ODE, right? So I don't need a distance. And the point that we are working with the weak convergence, which feels right. And there are a lot of distances which gives you the weak convergence. There are all the scales of Wasserstein-Morse-Contorovich distance. There are a lot of them, and we will use one of them, which is W1. You have the Prohorov metric, and you have a lot of variants. I guess there is a book by a Russian guy, Radic, something like that, which maybe he studied maybe like more than 150 or 200 metrics giving you the weak convergence. So really there are a lot. You have metrics based on Fourier transform introduced by Toscani and Villani at the beginning of the 2000, which works very well, which is very useful too. So you have the bounded Lipschitz norm, which is a variant of W1, which works well when you don't deal with probability measure, but with measure with varying mass, or which can change sign. So there are a lot of stuff. But W1 is nice to work with. And so the distance W1, it's W because it's for the Wasserstein distance, but they are also called Morse-Contorovich distance because they appear very naturally in optimal transportation problem. And in optimal transportation, Morse and Kontorovich are maybe the founder. So maybe more right to call them Morse Kontorovich. But I stick with what I saw in papers, they call it W1. So okay, so this distance W1 may be defined. W1 has two different definitions which are equivalent, and I will use this one, which is by my practice, I guess it's the most convenient, the easier formulation to work with, and it's just taking that we just take the supremum of the integral of phi against mu minus nu, okay, and phi can be any Lipschitz function with Lipschitz constant less or equal than 1. Yes, also clearly something like that. Phi must verify that. Okay, so it's very close to the total variation norm. except that in the total variation now, the test function phi was only required to be between -1 and 1. Here it's different. You need one function to be one Lipschitz. Okay. And this is not the very first definition of the Monge-Kantorovich distances. I will give, I guess I will need it later, maybe tomorrow. But it's equivalent through the Kantorovich-Rubinstein theory. Okay. So just if you're interested in all that referring to optimal transportation, a very nice book is Cedric Villani's book, Topics in Optimal Transportation, which deals, where it presents all the theory of optimal transportation. And there are maybe 2 chapters about Monge-Kantorovich distances, and well, a lot more than that later. Okay, so there is one piece of technicality, which is that just look at, if you take a Lipschitz function, a Lipschitz function can grow at most linearly, like x at infinity. So for this expression to be well defined, you need to work with measure satisfying this kind of condition. Okay. Yeah, you can say that they have a finite first order moment. Okay. Usually, you don't care much. You can just drop that by working directly with measure with compact with compact support. And for us, when dealing with transport equation, this is not a big issue, because since in transport equation, the movement occurs at finite speed, then if initially my measure has compact support, then at any time t, my mu t will have compact support. So I will be good, right? But in any way, you need to work for this kind with this kind of measure, right? And what you can prove is that this W1 is truly a metric. It satisfies all the axioms of metric. And with this metric, it's this space P1 is complete, which is pretty nice. And the convergence with respect to this metric is equivalent to the convergence for each text against test functions phi, which grows at most linear. So again, when we are dealing with compactly supporting measures, then we don't care much about that, and we will cover that, and we got the convergence for any bound continuous function, which is exactly the weak convergence. Okay. So, but this distance is pretty usually it's very easy to work with, very friendly to work with. So it's pretty neat. Okay. In comparison, in optimal, the classical theory in optimal transport theory deals with another distance, which is W2, which is maybe more sweet. Okay, but here for us, W1 is good, very good. So let's say how we could use this distance to get some estimation of the distance between my 2 solutions, mu t and nu t. Okay, so this should be nu t equal to the push forward of nu naught. Just I completely forgot. I copy paste and I forgot to change nu for nu. So this should be a nu t, and this should be nu naught here. Sorry for that. I will correct it later. So yeah, I got these 2 initial conditions, mu naught and nu naught. I got the 2 solutions, the 2 unique solutions of my equation, mu t and nu t, and I want to compare the distance between nu t and nu t. So I pick a test function, a phi, which is 1 Lipschitz, yes, and I want to estimate this integral, because later I would want to take the supremum of this integral over any phi, right? And I would very much like to make the distance between mu naught and nu naught to appear on the right hand side. So first, just by the very definition of the push forward here, this integral is this one, exactly. This is a definition of the push forward by the flow T sub t, right? Then what I do is that phi is what is Lipschitz. T sub t is Lipschitz 2. We'll check that. It's very easy. So this is a Lipschitz function. But to be admissible in the definition of W1, my Lipschitz function should have Lipschitz constant equal to 1 at most. And well, this Lipschitz function may not have a Lipschitz constant at most 1. So I just normalize, right? I divide by the Lipschitz function and multiply by the Lipschitz function. That way, the nice thing here is that now this function here is Lipschitz with a Lipschitz constant or at most equal to 1. So it is admissible in the definition of the W1 distance between mu naught and mu naught, which means that this integral here is less than this distance. So this is good. Now, the only thing I need to check, which is very elementary, is I want to check what is the Lipschitz constant of this thing here, right? So we do this very easily. Yeah. Just I look at this function at x minus my function at y. Use that phi is 1 Lipschitz, and then I need to check that this flow is Lipschitz, which is easy, right? Because you just have to remember that should have wrote it here. Just have to remember that T sub t initially is equal to x, and its derivative is the vector field v. Tac, tac, tac. So if you use that to estimate this expression here, you get the next line, and we use the fact that v is globally Lipschitz to bound the integral. And now, to conclude, we only need, if you look at this inequality here, that this thing here, we could apply Grunwald inequality. Easy, right? Because the function we have here is exactly the one we have here in the integral. So if we do that, if we apply Grunwald inequality, we can bound this expression T sub t of x minus T sub t of y, and so we can find the bound on the Lipschitz constant of my function phi of T sub t. So let's write that. Okay, so Grunwald inequality first gives me this bound, and then I deduce, when I put that here, I deduce a bound on the Lipschitz constant of phi of T sub t, which is this one. Okay, coming back to the very beginning of the argument, we got that. Okay, so this is good, because the bound we have on the right hand side do not depend on phi. It's okay for any one Lipschitz phi. So we can take the supremum of a phi, and the supremum of a phi of the left hand side, that is the supremum of a phi of this expression, is exactly the W1 distance between mu t and mu t. So we're good. We have exactly what we wanted. A bound of the distance between mu t and mu t, we can bound it by a constant, which is growing exponential in time, times the distance between the initial condition. So it's good. We have exactly continuity with respect to the initial condition. Okay. We should just to be able to use this W1 of mu t and mu t, we should check either that mu t and mu t belong to P1, that is have finite first order moments, which is true, you can check that. Or if you don't want to bother, we could just assume that mu naught and the initial condition mu naught and nu naught are compact support, and then mu t and nu t have compact support too, and we are done. Okay, so just depends, but this is all technicality. Essentially, we are good. So if we summary everything, what do we have? We have a complete well-posedness result for this kind of transport equation, starting from any initial condition, which could be any probability measure. We have existence uniqueness in this class of functions. For the existence, we have the explicit expression of the solution, and we just obtain precise estimates of the distance between two solutions with respect to the distance between the initial condition, mu naught and mu naught. So this is pretty complete and easy. If you look at all the steps of the proof, they are very, very simple. What I wanted to show what I wanted to do is not to show you the full proof in 2 slides, but to gently get there, to arrive at that point, but understanding what are the assumptions, what we're doing, only that. Well, and this kind of result can be extended in a lot of directions. Yeah, one direction we will be looking at now is when V depends on the solution mu itself, and this is relevant, right? In a lot of problems, we'll see one example now, right? And tomorrow we'll get another other equation where V explicitly depends on the solution mu itself. Okay, so we need to extend this kind of result to this kind of vector field. Okay. Another possibility would be to add some to replace the right hand side, which is for now is 0, by some expression which could be something like that, something like should be, let's say, some term here, which could be a growth, which could incorporate a growth, a birth term, and a death term. A death term would be something like that, something like a death rate time mu, and we could have some birth term. Okay, this is especially relevant in biology, where mu represents the density of some animals of a given characteristic. You can structure your population by age or by size or by any characteristic, phenotypic characteristic, anything you want, right? And in that context, you have to take into account that animals are dying and appearing. Okay, and maybe the birth term is not that easy, because it could be something like that. Imagine you have a population, you structure by let's say age, right, or size. Okay, so you are in 1D. Okay, mu t is the distribution of your animals with size, blah blah blah. Okay, you can add a growth term, which could be something like that. Okay, which could itself depend on the whole population, because you could say something like, well, if my population is big, there are not enough resources for everybody, so they are not my animals are not growing in size as fast as before. But when the population is small, there are a lot of resources, everybody has a lot of food, everybody is growing in size quickly, so your growth size could depend on the whole state of the population, your mu. You could add a death term here, And again, the death coefficient could depend on you. If if the population is big, there are a lot of competition among individuals to get resources, so maybe they are dying faster, right? And you could add some birth term. But what happens when individuals are born? They are born with a size equal to 0, and then they are growing inside. So you need a direct mass here to say that your newborn individual has size equal to 0, and then you can put any term you want for the birth size. So it could be something like that. For instance, could be, let's say, the mu t. You look at all the population, and depending on the size of the animal, it may have some particular reproduction rate, birth rate. Right? You could add some mutation here too, right? You could say that some animal of that type may give birth to animal of another type. Okay, so you have a lot of variants, but I mean, from a biological point of view, it's very natural to add a source term to in the right-hand side of your equation, which can be a measure in general. Okay, here I wrote an example, and so in everything can be generalized to this kind of set. Okay, maybe it's more technical than complex. Okay, but the general idea is always the same. Just follow the trajectories of the vector field, and just, well, maybe also computations, estimation will be a little bit more involved, but it won't be that essentially it won't be that complicated. But it's very relevant, right? And there are a lot of other issues you can discuss. You can discuss, for instance, numerical schemes for this kind of equation. And your numerical scheme should be able to keep track of direct masses, or keep track of the smooth part of your measure. So it's not that trivial. It's a pretty new area. Or you could look at how sensitive is your solution with respect to the parameter of the model. How sensitive is the solution with respect to the death rate, or the birth rate, or my growth rate, right? And you need to, it would be nice to have a sensitivity equation for the derivative of the solution with respect to this parameter. And you can do that, but the functionality, the functional framework is a little more involved, right? It's a little more tedious. But I mean, there are a lot of work you can do around this kind of equation, which are meaningful from a modeling point of view, right? Okay, so what I would like to do now is to see what happens when the vector field itself depends on the solution of the equation. How, first, why do I care? Why do I bother with this kind of equation beside for mathematical sake? Right? Because first, tomorrow we'll see natural equation, the dynamic opinion formation, dynamic of opinion, giving rise to this kind of equation. And now I will show you another kind of situation, more biologically motivated, giving you this kind of equation. And then we'll comment briefly on what usually you do to get existence, uniqueness, and so on. But very, very briefly, because it's not very complicated. It could be a little bit tedious to write down everything. So, but I will give you some references, nice references. It's not complicated. So let's see just an example of where this kind of equation, where vector field do appear. So just let us do that for the next 15 minutes. Okay, imagine you have a big bunch of individuals. Okay, and each individual some way is characterized by some parameter. X1 for the first individual, X2 for the second one, and so on. Okay, and these parameters will change in time under the influence of the rest of the population. And I will assume that every animal, every individual feels the rest of the population more or less in the same way, in like a mean way. Meaning that if this function k gives me the influence of an individual at y over an individual at x, then globally an individual will feel the mean value, the mean forces of all the rest of the population. Right? So you see, this is no big deal. If k is Lipschitz, you have a nice system of ODEs. Good. We'll see in the next slide. I will show you an example of that, which is Cooker-Smale flocking model. But the thing is that if your population is big, meaning if n is large, you have a big system of relays, which might not be convenient which might not be that easy to analyze or to simulate. If you have a big bunch of ODEs, it may take some time to simulate it. Okay, so the next question would be, okay, maybe we could find a way to simplify this system when n goes to infinity, to compact everything in one single equation, which will be a partial differential equation of this type. We only have to identify the vector field. As a vector field, obviously, since the vector field drives the dynamic, the vector field will have to do with the k, because the k is telling me how an individual influences another. Okay, but I would like to see precisely what should I put here to make something which would condensate this system into one equation. So let's see one example, one relevant example, which is a flocking model due to Felipe Cooker and Stephen Smale in 2006, which generated a lot of works and still generates a lot of works, because it's a very simple model where you see, if you just imagine you see some birds in the sky, like goose or ducks, and you see they are all flying like in a V formation, all regular, all maintaining the same velocity of movement, all maintaining more or less the same distance between one duck and the neighbors. Or if you think of those swarms of bees or fishes, where a big bunch of fishes is moving in the same way in the sea. Okay, this kind of flocking behavior, it can be modeled very easily using this Cooker-Smale model, which is nice because in this model there is no big director organizing the movement of the whole population. Instead, the very nice organization of the population is only the resultant of very simple interaction rules between the animals. Here, in that setting, my animals has two parameters, its position and its velocity. So the derivative of the position is the velocity, and the derivative of the velocity is very easy. What I will do is I want to align with my neighbors. So I look at a neighbor, for instance, this one, and I look at the difference between its velocity vector and mine, which is this one. And I take the mean of all these differences among all my neighbors. Okay, except that maybe I will just look more carefully at the neighbor I have close to me than the neighbor who are very far away from me. So this is the meaning of this term here, which says that if another if a neighbor is far away from me, I will not take him into account that much. Instead, if a neighbor is very close to me, it will matter a lot, right? But essentially, I will will try to take the mean of all the direction of my neighbors and align with respect to that direction. And what Cook and May proved in that paper of 2006 is that if beta is low enough, meaning that any individual takes into account in some way the rest of the population, then really all the birds are, as time goes by, tends to align their velocity vector and tends to maintain constant relative positions. And this is nice because there is this macroscopic organization of the whole group of birds is only the resultant of small adjustments made by each bird individually. Okay? And here in those papers here, you can find a very simple proof of that in 2 pages using only very elementary techniques of ODs. So this is not complicated at all. And well, but in that case, if you think of a big bunch of fishes in the sea, or a big bunch of bees in the sky, or or locusts, there are big cloud of locusts in the sky. They all have like the same movement, but from far away, it seems like maybe like a fluid. Okay, you cannot differentiate each individual. It's more like a big fluid moving along, deforming and everything. And it would be nice to get this kind of continuous description of this big OD system. And this is a very classical topic, an old topic, going back at least to the 80s, but still giving rise to some investigation, especially when K is not regular. When K is singular, as like a gravity interaction, this is not trivial at all. Okay, you can look at papers by that subject by Pierre-Emmanuel Jabin, and for instance, there are just a few names, and Golf, François Golf, okay, and their web pages, but there are 2 names among many, right? Okay, so if you're interested, right, just okay. So to do that, the classical trick is to forget about each individual individually and to look at the pack, at the group. And you do that by looking at the empirical measure, which is this one. You put a direct mass over each individual and you take the mean. That way you have a probability measure. The nice thing is that now you are not working in a big dimensional space. Because remember, if every x belongs to RD and I got n x's, I need to work in RD to the power n. So it's too big. Here with that trick, you only need to work in one space with a fixed dimension, let's say, but it's a probability measure. So it's not that easy. But the dimensions of the space do not vary anymore. This is good. And this mu-t do satisfy an equation. And to find it, we do the same thing as before. We multiply mu by test function, integrate, and take the derivative. And here this is quite easy because mu is a convex combination of direct masses. So this integral is only this thing here. We take the derivative, which is this one, and we rewrite back this sum as an integral that way. And now we get our vector field. This is our vector field. If my population is distributed according to this probability measure mu, then someone at x will globally feel the mean value of the forces exerted by any individual in the population. So I pick an individual in the population who at y, and it influences me that way. Then I take the mean over the whole population, and I get the mean forces I received from the population. This is my vector field, right? Because if we come back here, we can rewrite everything in that way. just that way here. And this is good because if you think this is your V, then here you have the weak formulation of the transport equation we were studying before, right? Which is this one. So that's nice. But you see that things get complicated because now my transport equations, the vector field in it, do depend on the solution itself. Because all the population influences every individual in the population, which then changes its direction. There is a retroaction between each individual and the whole population, right? And this is a very common situation in physics, where each particle produces a field, and each field do influence the whole population. Okay, so this is a very classical situation. This is not at all uncommon. But here I wanted to give you this model of the motivation for this from the Kuckersmein model, because it's a very interesting model, which generates a lot of investigation. And by the way, if you are interested about the flocking model, you can look at the page of Ethan Tanmore here. And there is a Korean guy, Shama Ha, but I'm not sure, I'm maybe confused. Yeah. But there are a lot of words about that, and all these flocking models are very useful in concrete application, and also in simulation of used in movies, for instance. Okay. So the main idea here is to think of a big population initially modeled through a big system of ODE to obtain like a continuous description of this population, to think of it like a fluid, right? And the equation which expresses the continuity of mass, only moving, but not mass being destroyed or added, is given through this kind of equation here, right? And if informally we send n to infinity, in that case, this measure should, at least for any time t, would converge to some measure limit mu t. Then this mu t would satisfy this equation. And it would be very nice to have some kind of existence uniqueness and also a continuity result with respect to initial condition. Let's say how we could do that. Right? So I hope I convinced you that studying this kind of equation is interesting, is relevant. Nice. So now the question is, how do you get the solution? And what kind of assumption do you need to make on your vector field, right? And so I won't put much detail here. I will just give you some references and just give you a feeling, but it's not complicated at all. I can assure you that. You only have to rewrite the equation as a fixed point problem, right? Because for imagine it's very easy, because imagine you fix the mu here, only the one inside V. Imagine this mu is fixed. Then you can solve the equation. Yeah, it's this one. We know how to solve that. But now what we want is that the solution we get should be exactly the mu we fixed inside the vector field V. So, which is this one. So we get this fixed point formulation. So this means that we only have to obtain a fixed point for this kind of map here. And you can do this very easily using just Banach fixed point theorem, just checking that this gamma will send some convex subset, complete convex subset into itself, and will now a complete space into itself, not convex, I don't need that. And we should need some strict contractivity property. but it's easy. So putting some assumption on V with a nice V global leaf sheet and everything, it's easy. With less regularity on the vector field V, it's very complicated. It's complicated. Okay, and just I put here 2 references on that. There is a very, very nice survey by Gors, which is published in some journal, but you can find here the preprint, and it's very, very nicely written, very interesting. And you would want to check the web page, of course, for nice papers and everything. And there is, and going back to the Cookers main model, there is a nice paper by Canizo, Carrillo, and Rosado, which appeared like 10 years ago and very high type too, giving you exactly the full proof of that for the Cookers main model. But really, you just have to, if you understand a simple transport equation with a given vector field, and you understand that you have to write everything as a fixed point problem, you're almost there, right? The rest is only slight technicalities, but nothing very complicated. Okay, so, and also you have continuity with respect to the initial condition. Okay, so you have a full well-posted result. And the nice thing with that well-posted result is, if we come back to, we can really justify that this equation is, in some sense, the right limit of this system of ODE, because we saw that we could condensate the whole system of ODE through the empirical measure to this equation, right? So now, assume that we have some initial condition mu naught, which is an arbitrary probability measure, right? We can approximate it by some convex combination of direct masses of this kind. No big deal. Right? Then, for this one, we can solve this equation for both initial conditions, for the true initial condition and the approximate initial condition, right? Okay, and since the problem is well posed, since this equation we have continuity with respect to the initial condition, then this means that from that we get that for any time t, the solution of my implicitly of the system will converge to the solution of this equation. So in that sense, we could really say that this system, this equation, sorry, is the right limit, the right way to obtain to speak of the limits as of the system of ODE as the number of equations grows to infinity. And the other thing which is quite nice with this continuity with respect to the initial condition is the fact that if we come back to the Cookers main model, then once we can prove that using ODE techniques, once we can prove that all the birds are asymptotically flying all with the same velocity, maintaining constant relative positions, then we can translate these properties to any solution of the transport equation, where K comes from the system of ODE. So this is pretty good, right? Because really studying the system of ODEs in the Cookers main model is not complicated. Just look at the 2 references I put, and it's not complicated at all. It's very elementary. But you can pass these properties for any solution of this system, for almost any, maybe with assuming that the initial conditions as compact support, maybe. But you can pass everything. So this is pretty neat. Right? And tomorrow, just to give you a feeling of what we'll be doing tomorrow, we'll see another approach to model the dynamic of opinion of an opinion dynamic, more based on a kinetic approach. And we'll be following papers by Giuseppe Toscani and Lorenzo Paleschi, right? And we'll see with some simulation what we can get and write an equation very similar to the master equation we wrote yesterday, and see what we can do with that, and how, when you complicate a little bit the modeling framework, the equation becomes quite complicated, and how you can try to simplify things a little bit. And then at that point, we will come back again to this kind of equation. But now, since we have a feeling of how the vector field is driving the dynamic, we will be able very easily to understand what happens. And then, well, we still need to prove something rigorously, but I won't do that part, just to give you some references. Okay. And with that, I guess we'll be seeing a lot of modeling as theoretical tools. Okay? Okay, so I guess for today, this is all I wanted to share with you today.